I'm going to talk to you guys today about DevOps and Industry 4.0, which is sort of the next evolution or revolution in the industrial space. There's a little bit of echo on the mic. So just a little bit about myself. I started out probably like many of you in the technology space as an IT consultant for many years. I spent a fair number of years in the Montreal startup community at companies like CoRadiant. I was a founding partner at CloudOps and then started my own cloud services company called Hybrid Cloud Gateway. About 6 years ago, I was interested in getting into the IoT space, which was really just emerging at the time, and got introduced by the CloudOps guys, actually, to the CIO of Alcan, which is based here in Montreal and is the second largest aluminum producer globally, and a part of the Rio Tinto global mining family, Rio Tinto being the second largest mining company globally. So now, instead of chasing the latest phone and stuff, these are really the new toys I like to play with. The industrial space is fascinating and undergoing rapid change at the moment, thanks in large part to developments in the traditional IT technology ecosystem. And now we're starting to take a lot of the learnings from the DevOps community and Agile and apply them in industrial contexts. So I'm going to talk about that a little bit, hopefully introduce you guys to some new streams of technology you might not have been exposed to previously, and then we'll talk about sort of the future of DevOps and how it's going to change manufacturing and heavy industry going forward. So I'm sure most of you are familiar with this quote from Mark Andreessen: software is eating the world. And this manifests itself in many different ways. I think as consumers of technology, we see it every day in how we interact with each other, how we do commerce, even how we're starting to interact with our homes. Another aspect of this is how things are starting to affect the industrial space. And I want you to keep in mind that everything you have, everything you own, everything you're wearing was either, the materials were either grown or they were mined and manufactured, processed in some way. So really, everything comes down to how software is affecting all these different areas and the impact it has. So for instance, this week in the news, you guys probably saw some images of this. This is an Irving oil refinery that blew up in St. John's, I think yesterday or the day before. This was a software failure. The emergency control systems that should have been on and operational in the plant were not, because the plant was in what's called a shutdown state. They were doing maintenance on the plant. This was a planned maintenance window, a planned shutdown, and yet they didn't take all the necessary precautions, and their DevOps or software failure, depending on how you want to look at it, it caused an actual explosion. And this is the type of reality we deal with in the industrial space. It's not just about revenue, number of users, click-throughs, and availability of systems. Really, people's lives are in the line of fire. And so it takes a bit of a different orientation, and we'll explore that a little further. So title of the talk is about DevOps and Industry 4.0. Industry 4.0, again, it's sort of an overloaded term these days. But if we look at sort of the first three industrial revolutions, here we've got an overview and the times that they emerged. These aren't the times they lasted. And right now, we're sort of in between the third industrial revolution, which is around telecom and PLCs, programmable logic controllers, and Industry 4.0, which we'll discuss in a little more detail. So steam, everybody's pretty familiar that this was the heart of the first industrial revolution. All of a sudden, we could create these mechanical machines that could do work that humans or animals used to have to do previously. And the steam revolution really helped solidify a lot of the ideas around automation. But during this time, this was your automation. It was these guys who went out. When a valve had to be open or closed, one of these guys ran and closed the pump. When the steam boiler needed more energy, they would go shovel coal. And that's the way things worked. This is what data collection looked like at the time, right? Standard ledgers, really bad retrieval and search functionality. But then we hit the second industrial revolution, which was really electrification. And suddenly you can see the density of the factory floor got much more compact, tighter. We were able to stick many more machines in the same space, but still the processes were entirely mechanical in nature. We were just using electricity as a substitute for steam in a lot of ways, and we didn't change how we did things. But with electrification came the ability to control the electricity. And so a lot of what was automation at the time was handled through systems like this, which are essentially electrical relays. And suddenly you could remove some of the control from right at the machine face and have it in what's essentially today would be a server closet of some sort, where you have these relays and you can remotely power on, power off machines. This is the first time series database. This is a mechanical data recorder. And you can see there's the times around the outer rim. And we have these pens that basically the paper moves around on a clockwork, right, keeping time with the actual time. And as the production values affect where the marker is on the thing. And this was your historical record of your production capacity, what you did, how your plant was operating. Then we hit the third industrial revolution in the early 60s. And this really became around about electronics and automation. And so we see these industrial robots on an auto manufacturing line. But these are really simple robots in a lot of ways. In fact, they only do one task. Everything has to be perfectly aligned for them to be able to do that task properly. The entire system is very fragile. And yet, the productivity gains by even just this level of automation were huge. And this is how a lot of plants that are being built today are still using this type of automation paradigm. Now, you have to understand, when you build a factory, its lifespan is minimum 30 years and probably 30 to 60 years in preview. And so we've had an entire industrial revolution from the beginning of the third industrial revolution to the beginning of the fourth industrial revolution where we are now. And some of those factories have never reached their end of life within that time span and are now looking for future upgrades or to be rebuilt. And they're skipping an entire generation, which leads to some interesting opportunities, particularly in places like Africa. So in Industry 3.0, the workhorse is the programmable logic controller. This, for those of you who might be familiar with an Arduino, is similar in behavior, if you will. It's got a scan time generally measured in microseconds, and it's got a guaranteed scan time. So it runs through its entire program within a guaranteed number of microseconds, regardless of what code is actually being executed. This is ladder logic. This is how you program a programmable logic controller. So this was a programming language developed in the 60s for electricians. And you can see it looks like an electrical schematic. But this is how we program even today. This is ladder logic on a modern platform. This is how you still program PLCs. Now, PLCs, for those of you who are unfamiliar with them, are everywhere. In fact, you interact with them probably daily, if not multiple times a day. Every elevator you ride in, every escalator, most of the automatic doors, every bus, every metro are all controlled via PLCs. And so, again, in the manufacturing industry, these are the workhorses. But in the 80s, when PLCs were being deployed on the plant floor, we were still seeing data historians or time series data being collected like this. Why was that? Because, again, in the early 80s, 1 gigabyte of storage was about $1 million versus a few cents today. And so the data historian, or the original time series databases, were super efficient at storing time series data. But don't forget, these were 8-bit and 16-bit computing platforms that were being used at the time. So to measure the voltage in an aluminum smelter and record that in a meaningful way, you need much more bit depth than 8 bits for your values to have any significance or to be relevant at all. And so these early time series databases called data historians, OSISOft Pi being the market leader, are still found throughout almost every factory and industrial process today. And this is what the OSISOft, these guys have about 80% of this market share. This is what their ecosystem looks like today. So you've got the traditional stuff that they've always done, but now starting to pump data into Hadoop and other big data platforms and make it more available so the data is no longer siloed. So this is Industry 4.0. Industry 4.0 is really about cyber-physical systems. So these are systems that are aware of each other and don't require an operator in the loop for them to make decisions and actually fulfill their production missions. So it changes the automation pyramid, which is a traditional way everyone's taught and learns about automation. And these systems now are talking to each other. So a lot of the paradigms that the guys on the factory floors are used to are disappearing, like the rugs being pulled out from under their feet, and they're struggling a bit. And we've seen this in the IT industry quite a bit. The analogy I like to use is like with the telecom guys. The way dev and ops used to be two separate functions, telecom and IT used to be two separate functions. Today, we have in the industrial space OT, the OT guys, operational technology guys, and the IT guys. And they have very different areas of responsibility and ways of looking at the world. So as I was mentioning before, the OT guys are really concerned about human safety and property safety. And constraints are very different as well. And even security priorities are rather different. So we don't have time to go through all of these, but there's quite a difference in mental shift that's required to operate in an OT environment compared to a traditional, fully digital software environment. And now what we're seeing is this convergence of IT and OT. So quickly run through DevOps and how it's being applied. We've got new design patterns. So you can forget all the nice cloud stuff that you guys are probably familiar with on the left. But here we've got IoT gateways attached to PLCs and edge nodes directly. And we can push containers with logic that run locally attached to the PLCs, but are managed from the cloud. And so this changes the entire programming of a factory floor from the ground up. Now the PLCs can have really just the safety and basic control logic, and these containers that are sitting at the edge can actually have all the business logic, even the manufacturing recipes, and dynamically reprogram the PLCs as required. This is another cloud, PLC to cloud type of architecture that's starting to emerge. But these are all pretty new developments. Code management and development. So again, we saw this piece of code. Git doesn't support ladder logic. And so you run into finding version control on the factory floor is actually a rarity. So some PLC programmers, I mean, you'll find like versions of Subversion out there scattered here and there. But the industry standards in the OT space really haven't adopted some of the best practices that we're aware of. And so even if they did, though, things like a ladder logic program, right, you're doing file-level version control as opposed to being able to break out your logic and have different dev teams work on different pieces. But we are starting to see early adopters who are moving their PLC code to repositories like Git and making things available. Extreme programming for PLCs. This is something I ran a study with Accenture on about 1.5 years ago. Super interesting. Every plant that we proposed this to was vehemently opposed. 2 programmers to give me 1 set of functionality. Why am I paying for that? Our study with Accenture found that we actually had 25% reduction in errors and close to a 30% increase in overall productivity. Errors in a PLC are major events. So the test and dev pipelines, which we'll see in a second, aren't what you guys are probably used to. And so when you've got an error, so for instance, one operator pushed PLC code he thought was going into a dev environment into production, causes a factory floor shutdown. That's a $4 million mistake and potentially has huge safety implications for the users. CI/CD pipelines, again, this is like cutting edge stuff. This TwinCat software is relatively new and not widely adopted or respected yet, but we're starting to see these type of things emerge, and this is where there's still a huge amount of opportunity in bringing DevOps practices into the industrial space. Testing. So this is a standard PLC test environment where the guy loads his code into the dev machine and very manually flicks the switches, adjusts the knobs, makes sure the code reacts as expected. We're starting to see emulation and testing as sort of an emerging trend now. And simulation becomes very important, especially with autonomous systems. So sometimes perfect is not good. So for instance, automated haulage systems, so haul trucks, big dump trucks that carry 3,000 tons of ore. When they're fully automated and using RTK, basically high precision GPS for navigation, our initial tries at getting these deployed was very successful. They were always at exactly the right position, and human interaction was great. As we scaled up, and this was a scaling issue, as more of these automated trucks were using the same roads, we noticed they were too perfect. They were all traveling up the haul road at exactly the same point. And so they were digging a groove in the road because they were all centimeter precise in the same place, always traveling in the same path. So we have to go back in and introduce variability and randomness into the AI algorithms in order to smooth out the usage of the roads. Each of the tires on a haul truck like that's about 35 to 45,000. So 6 per truck, it adds up quickly. Reliability engineering, again, we don't have time to go into it. Who watches the watchers? The real world is analog. Most of the sensor signals you're getting could be totally wrong. We get sensor drift over time, and now we're starting to apply AI algorithms to physical analog sensor data in order to predict at different parts where the value should be and whether the sensors are actually operating in the way that you intended them to and with the same calibrations. So if you want to get your feet wet in the industrial space, there are a few interesting projects you can get involved with. There's C3PO up here in the left, which is a great Python library for communications from standard IT systems to programmable logic controllers. Apache has just started sponsoring, it's in incubation right now, very early, a similar project called PLC4X. And then there are things like the OpenPLC, and Udemy actually has some great PLC programming courses if you want to learn ladder logic. Anyhow, I hope that was of interest, and thank you very much.